Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the exact same problem that we solved just a couple days ago, implement string, but instead of solving it with the brute force solution that we did last time, which was about n times m, we're actually going to be doing the much more optimized solution using a very standard but also very complicated algorithm called the KMP algorithm for short. The time complexity of it is much better. It's actually big O of n plus m, so much more efficient, but the downside is it changes this problem from being an easy problem to honestly being a very, very hard problem, especially if you don't know what this algorithm is. It's basically impossible to come up with it yourself in a short amount of time, but if you learn it ahead of time, you should be able to implement it. First, let's just quickly review through the brute force solution and kind of understand the motivation for this KMP algorithm. Remember, the brute force is going to take a substring. In this case, we're going to call that the needle, and the original entire string, which we're calling the haystack for the context of this problem. We want to find a matching needle substring within the haystack, right? First, we check the first three characters. Do they match with the needle? Nope. Then we check the next three characters. Do they match? Nope. The next three, etc., etc., right? We're basically checking every substring of length 3 in the entire string. So that's what makes the time complexity really inefficient, basically multiplying both strings together. But in reality, this brute force solution actually runs better than this. Take, for example, the two strings we have up above. First, we're just going to compare the first characters of each string, right? A and X, to check if this substring is equal to the needle. In this case, the first characters don't even match. So of course, we don't even have to check the next two characters, right? So next, we want to know if this matches the next three characters. So we just check the first characters. They still don't match. So we'll do the exact same thing with these three. The first character doesn't match. Then we check these three. The first character again doesn't match. So in this case, this string was never found in the haystack, and in reality, the time complexity was actually big O of n, where n is the size of the haystack. It wasn't very inefficient at all, which kind of shows you that KMP is not even super useful most of the time, but let's take a look at an example where it will be very useful. So this is a very specific example, which kind of is necessary to illustrate the KMP algorithm. But in this case, if we try doing the brute force solution without KMP, we're going to check the first four characters. Do they match the substring we're looking for? Well, the first character does match, the second character does match, the third matches as well, but the fourth is an X when we actually want an A character. So this doesn't work. And we had to actually go through the entire needle just to find out that the last character didn't match. That's pretty annoying. And next, we're going to go through these four characters. In this case, we're going to check the first two characters only to find that the third one does not match. And that's kind of the theme of these two strings, right? Next, we're going to check here. Okay, not too bad. We only had to check the first character, which does match, but then the second one does not match. Next, we check this. Okay, the first one doesn't match. The X doesn't match. Okay, not too bad. But then we kind of get the same thing that we did at the beginning. We have to go through all three characters just to check that the fourth one doesn't match, right? So this is an example where the time complexity the runtime is actually pretty bad. It's about n times m. And the KMP algorithm actually can solve that problem for us. It will ensure that the worst case runtime is going to be n plus m. The downside is it's very, very complicated, but I'll try to explain it in a way that you won't have to memorize too many of the details. You'll be able to allow your intuition to guide you to the solution. So the main idea is to cut out some repeated work by doing some pre-processing. So we saw that we first compared the first four characters of each of them. The first three characters did match, but then we got to the fourth character, which did not match, right? And then we had to start all over again. Then we had to compare these with our needle. And we had to start at the first character of this substring, right? We had to go back to the beginning of our needle and here. But is that really necessary? Because remember, it was this character that actually gave us trouble. It was the X character. These characters were perfectly fine. And not only were these characters fine, these characters actually still match the beginning of our needle. This prefix matches this prefix. So why should we have to go through these characters again? In reality, our pointer in the haystack should still be at the X character where we left off, where we found the mismatch. And our pointer in the needle should be over here because the first two already match this. Can we somehow intelligently not have to do this repeated work again? And yes, there's a way. That's what the KMP algorithm's all about. And the first portion of this KMP algorithm is actually called the longest prefix suffix portion. Let's just call it LPS for now, but it has to do with prefixes and suffixes. Basically, for certain substrings, we're going to take a look at the longest prefix of that string that is also a suffix of that substring, and you'll see why that's going to be really helpful. Basically, that's what's going to allow us to somehow intelligently take this prefix and already know that we don't have to read through this again because it already matched a portion of the haystack and we don't have to go through it again. So for the needle itself, right, the pattern that we're trying to find within the larger string, that's what we're going to create the LPS array for. It's an array that's going to be the exact same size as the needle. What each index of this is going to represent is it's going to correspond. So for example, the first position of the LPS is going to correspond to this substring. The second index of LPS is going to correspond to this substring. The third is going to correspond to this, and the fourth is going to correspond to this. So basically every single prefix of the needle. So this is our substring portion, and for the substring, we want to know something about it. We want to know the length of the longest prefix of this little substring over here that also happens to be a suffix. By the way, for a string, let's just say this is our string, a prefix is every substring starting at the beginning. So this is a prefix, right? Just the first character. The first two characters is a prefix. The first three characters is also a prefix. And by the way, a suffix is basically the opposite. Every substring that ends at the last character. So this last A character is a suffix, the last two characters are a suffix, and all three characters are a suffix. So we want to know for this little substring with just a single A, what's the longest prefix that's also a suffix? Well, the string itself, A, is a prefix and a suffix, right? So can we just take the length of that and say 1 for the first position? Well, not exactly, because I kind of lied. We're not just looking for the longest prefix that's also a suffix. There's one catch, and the prefix itself cannot be the entire string itself. So in this case, we can't put a 1 here. We have to put a 0 because the entire string itself can't be one of the prefixes, and we only have a string of length 1. So basically what we've figured out is the first position of our LPS is always going to be 0. The next position is where things get a little bit interesting. So now the substring we're looking at is the first two characters because this is the position that we're at. So what's the longest prefix of this that's also a suffix except the entire string? Well, the first character is the same as the last character, so we can say 1. And the next position, it's pretty simple in this example. So we're going to look at this substring, which is the first three characters because we're at the third position of our LPS. So what's the longest prefix that's also a suffix? Well, the first two characters, right? The first two characters match the last two characters. So we can put value here too. And then when we're at the last position, we're looking at all four characters. The first three match the last three, so we can put a 3 in this position. Okay, we're not quite done with the algorithm yet, but we have kind of got an understanding of the first portion, which is the LPS, longest prefix suffix portion. So what I'm going to do for the first time in Leetcode history is actually dual screen this. So now we're actually going to be doing the code at the same time as we look at the drawing. Because this problem is so complicated, I think that's going to be really helpful for us. So first thing I'm going to do is just for the context of this Leetcode problem itself, if the needle happens to be an empty string, then we have to return 0, saying that the first matching index we found was at index 0. But now we can get to the LPS portion. So we're going to create an LPS array. Initially, let's set it to all zeros and set it to be the same length as our needle array, right? Because the LPS is always going to be the same length as the needle. Okay, so now we're actually going to use 2 pointers for this problem. We're going to use the previous LPS pointer which is basically going to tell us the length of the previous longest prefix suffix, quite a complicated term. And we're also going to have a second pointer, I, which is going to be the current character we're looking at. So originally, the previous LPS is going to be 0 and I is going to be 1. The reason we're saying that is because remember, in this position, right, it's always going to be a 0, right? That's why previous LPS is 0. And our I pointer is actually going to be starting at 1 at this index, at least, even though this value is a 1, the index of this is also a 1. That's why our I pointer is set to this position, but we haven't figured this value out quite yet. So let's actually reset this thing to 0. So now we can fill in the rest of this as we go. And actually, let's do an even more interesting example. So this is actually the example we're going to look at. We're introducing a C character because you're going to see why. It's going to make this a lot more interesting and also a lot more difficult. Don't say I didn't warn you with this KMP algorithm. It's quite complicated. So I set I equal to I, but we actually want it to be equal to 1. So right, our previous LPS is going to be at 0 and our I pointer is going to be at this index looking at this character. So we're going to do a while loop, right? While I is less than the length of the needle, right? Because we're going through every character in the needle to fill in this LPS array. And so the simplest case is going to be if the characters match each other. So if the needle at index I is equal to the needle at index previous LPS. So what's going to happen in that case? Well, we're going to set LPS of I equal to the previous LPS plus 1, and we're going to increment now the previous LPS by 1, right? Because for the next iteration of the loop, we want it to be incremented by 1 because we just realized that these characters are equal. So we set the current LPS to previous LPS plus 1. So the value in here is basically what we're replacing the LPS with. And of course, we want to take this I pointer now and look at the next character at the third index. So we're going to go ahead and say I plus equal to 1. Now, these 3 lines of code actually are kind of complicated. Let's kind of go through this drawing and understand them. So how is it going to run, first of all? Well, we're going to compare these two characters, right? Previous LPS is here, I is here. These two characters are equal. What does that tell us? Well, that tells us that this is the prefix, this is the suffix. Since they're equal, we're going to take this and set it to be 1. Now what's going to happen on the second iteration of the loop? We set previous LPS to be at this position, and we set I to be at this position, right? We incremented both of them by 1. Now we're looking for the LPS value in this spot. So again, according to our algorithm right now, we're going to compare these two characters. They are equal again. So what are we going to put in this spot? We're going to take the previous LPS and add 1 to it. So we're going to end up putting 2 here, right? That makes sense. These two characters are equal to these two characters. So 2 is the right value to put here. Because remember, we can't use the entire string as a prefix. But how did this magically work? Why are we adding the previous LPS value plus 1? Well, that's the slightly difficult part. Let's explain it. First of all, when we determined that the LPS value here is equal to 1, what we actually determined was that this character, this prefix, is equal to this suffix, right? This character is equal to this character, this prefix, this suffix. So now when we're in this position, right, we're not manually going through the first character, checking if it's equal to this, etc., right? We're not starting all the way at the beginning because remember, our previous LPS value is 1. That tells us that this character already matches this character, right? So we don't even have to check this one because if we compare this value and it happens to be equal to this value, we already know that this matched that. So therefore, if this matches this, then we can just take the length of the previous LPS and add 1 to it, right? And this seems really complicated. Maybe you have an easier way you could implement this, but remember, our goal is to keep the time complexity to be n plus m. So we have to be able to do this needle LPS algorithm in O of n time, where let's say n is the length of this, and actually I'm going to be referring m to be the length of the needle. So that's basically why we use the previous LPS index or the previous LPS value to tell us what index to compare it to, because if this is 1, that already means that the first character matched this. So it's complicated, but let's quickly go through the rest of this example because it's about to get a little bit more complicated, because now we are going to have our previous LPS pointer be over here and our I pointer is going to be over here, and this is going to be the first time where we actually see that the two characters don't match each other. Clearly, we need to accommodate our code to deal with this, right? Because right now we only have the case where they do match each other. And within this else case, we are going to have one more conditional, and it's going to be if previous LPS is equal to 0, and the else condition where it's not equal to 0, because it's going to be a little bit different. Because as I was kind of talking about, right, this position, so we know that the previous LPS is 2. That means we already know this matches these two characters, so we only have to compare these two and check if they're equal. If they are equal, we can take this value 2 and add 1 to it and set this to 3. But what happens when they're not equal, which is the case right now? Well, first of all, let's consider our first case if previous LPS was actually equal to 0. Because right now our previous LPS is equal to 2, but let's consider a different example. Let's just change this really quickly. So let's just consider a different example for a quick second. Let's say we're doing the LPS of this. We know that the first value is always going to be 0. So right now we're comparing this character with this character. Are these characters equal? No, they are not. So we do our else case, right? And we look if previous LPS is equal to 0, meaning that there was never a prefix of this string that matched a suffix of the string. So that also tells us that the pointer that we're looking at is actually at the beginning, all the way at the beginning of the string. If even the first character does not match the last character, that means we can't possibly have a prefix that matches a suffix, right? So that means we can just put a 0 here. So that's the simple case. We're going to say that if previous LPS is at 0, then we can set LPS of I equal to 0. And also, let's not forget to increment our I pointer because we don't want to get stuck in an infinite loop. So we have our previous LPS here. That's what I'm going to use P to refer to. I is over here. The characters do not match each other. And previous LPS is not equal to 0, right? Our previous LPS is equal to 2 right now, so we're going to execute the else statement of this algorithm. And it's not actually going to make sense. This else condition is not going to make sense for this portion, but it's going to make sense when we actually finish this example. So remember, what this 2 tells us is that the first two characters matched the last two characters when we were over here. So we're trying to take a shortcut. We're trying to say if this character matches this character, then we can put a 3 here because that means these 3 match these 3. But if they don't match each other, that tells us the longest prefix suffix of this spot cannot be 3. That's what we were trying to check. Can it be 3, right? We were using the previous work that we'd already done. But now we know it can't be 3. But maybe it can be a 2 value, right? How can we check if it's a 2 value? Well, we're still going to leave our I pointer here because we're trying to fill in this spot, but our P pointer, which was over here now, it's going to be shifted to whatever value happens to be to the left of it, not necessarily decremented by 1, right? Decremented by 1 would be just putting it over here, then putting it over here, etc., etc. But we're going to move it to whatever value is to the left of it, which in this case does happen to be decrementing it by 1, but it's not always going to be the case, as you will see when we finish this example. So for now, we're going to take our P pointer and actually set it to be over here now. And what that tells us in the context of this problem is we're going to be using a shortcut to check, can we put a 2 value over here? Because we already know that this character matched this. That's what the 1 tells us, right? The prefix here was 1, so the 1 character from here matches 1 character from here. So now if we know that this character matches the C character over here, then we can put a 2 value here, right? We only have to make one comparison to determine that. But again, these characters do not equal each other. The A does not equal to C, so we can't even check that. Now we're going to take our P pointer, set it to whatever value is to the left of it. Right now it happens to be 0, so therefore our P pointer is going to be decremented by a 1. And we're basically now to the point where our P is all the way at the beginning of the string. So I was talking through this, but I probably should have coded it up at the same time. So let's just fill in our else case to set the previous LPS pointer to be equal to LPS at the index of previous LPS minus 1. Right, this is the value our previous LPS pointer is going to be set to. Notice we don't increment our I pointer here because it doesn't really make sense in the context of this drawing. And if it makes you feel any better, this actually is the entire code to set up this LPS array, even though it's quite complicated, but let's just run through the rest of this example. And actually, since we have an else if here, we can, condense this to this being an else if and this being an else. Okay, so now let's run through the rest of this drawing. So now our P pointer is here. Since this is a 0, that basically tells us we're not even using any of the pre-work that we did. We're directly comparing the first character with the last character. Can we at least put a 1 here? Is there at least a prefix of length 1 that's equal to the suffix of length 1? That's not even true though. The C does not equal an A, so we have to start all over. This is going to be a 0 value, right? And the reason we're putting a 0 value here is because now we're executing our else if, because our previous LPS is already all the way at 0, right? This is where our previous LPS is. We can't decrement it any further. So that's why it stays here. And we continue to the next position where our I pointer will now be over here. And our LPS is actually still going to be, our previous LPS is still going to be over here. Okay, now we're going to start building our way back up because this character does match this character. So we can set this to previous LPS plus 1. Previous LPS is 0, so we can set this to be 0 plus 1. That's going to be 1. We're gonna, and by the way, actually our previous LPS is also going to be incremented by 1 since we found matching characters. So this is going to go here. Right, and our I pointer was also incremented by 1. Now we're at this character. And what does this mean? Our previous LPS is at index 1, and the value at index 1 happens to be the value 1. It means that the first character already matched this character. That's why we incremented this to 1 in the first place, right? Because that's what we just checked. We checked that this is equal to this. So therefore, we only have to compare this with this over here to set this equal to 2, right? We're trying to shorten our work. They do happen to match. This matches this. So therefore, we can set this equal to 2 without having to recompare these. Right? We know that the suffix of length 2 here is equal to the prefix of length 2 here. And again, we're going to look at this character and this character. And by the way, our I pointer is going to be set to here now. Our P pointer is going to be here. That means that these two match these two already. So all we have to check, does this character at the P pointer match the character at the I pointer over here? Yes, they do. So we can put a 3 here. Now, this is the part where things are about to get interesting, the last index. So our I pointer was over here, right? We incremented it by 1. Our P pointer was here, but now we increment it by 1 to be over here since we found matching characters. And what we're trying to do, remember, is shorten our work. We know that these characters match these 3 characters. That's what we determined by this. So that's why we only have to compare this character with this one to be able to put a 4 here, but they're not equal, right? So that means we're going to execute our else case. Does previous LPS equal 0? It does not equal 0. Just because the value here is equal to 0 does not mean this is equal to 0. This is equal to 4, as you can see, right? It's at index equal to 4. So that else if case over here is not going to execute. We're going to execute the third case, and let's see what it ends up doing. So this pointer is going to be set to the value at the index to the left of it. So it's going to be set to 2, which happens to be this position itself, right? So our P pointer is now going to be shifted all the way over here. So now what does that mean? Because now the loop is just going to execute one more time, and it's going to run through these same conditionals. So now what are we checking now that our P pointer is here? What's different now? Well, since the value of this is equal to 2 now, what that means is the first 2 characters match these 2 characters, but now we're checking, does this character match this one? If they do match, which in this case, yes, they do match, we can take the value of P, which is equal to 2, it's at index 2, add 1 to it and then put that here. So we'll put a 3 here, right? We already knew the first 2 characters match. If this character matches as well, then we set a 3 here, right? We kind of cut down the work that we had to do. So that was a lot of work just to set up this LPS. And the time complexity of setting this up is actually just going to be the length of the needle times 2 in the worst case. I'll show you why. I won't talk too much why that is, but if you kind of, pick any example and go through this, you'll see that we don't, this is not exponential or like n squared or anything like that. Yes, sometimes we have to decrement our p, but if you took the example where we just have a ton of a's and then, at the end of it, we have like an x or something, the p pointer and I pointer will continuously be incremented by 1 each time. But when we finally get to the end, our p will be here, our I will be here. We're going to realize that, okay, these two are not equal. We're going to decrement our p by 1 over here. Again, we're going to see that this is not equal to this. So we're going to keep decrementing our p continuously until we get to here. I hope that gives you a little bit of the intuition of why this LPS is actually just 2 times n, not n squared. Okay, but that was a lot of work. So now let's actually get into the KMP portion of the algorithm now that we actually have our LPS set up. And let's actually start with the code at first. So what we're going to do is just initialize 2 pointers. I pointer is going to be for the haystack, J is going to be for the needle. They're both going to be at the beginning of each of those strings. And we're going to continue this loop until we reach the end of the haystack. But in reality, we're also going to be having an if statement within this while loop, because remember what this algorithm is trying to do is, at least for this Leetcode problem, we're trying to find a matching substring, this needle substring within the haystack. And if we do find it, for example, let's say we found it over here. If we just change this X to an A, this is the first place that we find this needle. Then we're going to return the index of the starting position in the haystack where we found it. So the index would be 0, 1, 2, 3, 4 would be the index of this. So that's what we would end up returning. So our pointers are going to be at the beginning of both of the strings. We're going to check, are they equal? That's the first thing we're going to check, right? Because we want to find all equal characters until maybe we find a mismatching character. So let's add that as a condition. So if haystack at index I is equal to the needle at index J, then all we want to do is increment both of the pointers. So I plus 1, J plus 1. And we probably also know that there's going to be an else case that's coming up if they do not match each other. So now our J pointers here, our I pointers here, again, they're equal. So increment again. Now they're here. Again, they're equal. Now we finally get to the else case. They are not equal, right? So before we even get into the code, let's just understand what we're now going to be doing. We were trying to check, is this equal to the needle? Now we know that the last character didn't match. So in our brute force solution, what we would want to do is now compare these 4 characters with the needle. And that's actually what we're going to do in the KMP algorithm as well. But in the brute force, we would end up resetting our J pointer to the beginning and have our I pointer also be at the beginning. But we're not going to do that in this case, because what we just determined right now is that this was the position that we found a mismatch at, right? This 4th position. So everything before that position was matching, right? This was equal to this. And now what we're going to end up doing is shifting by 1, looking at the next 4 characters. Take a look at this box because it's very important. The next 4 characters means that these 2 characters are going to be are consistent, right? These are the same 2 characters we were looking at before, these over here. So this was the last matching index, right? So now we're going to look at the position of our LPS at the last matching index, which is going to be J minus 1. So let me just write that in the code. LPS of J minus 1, that's going to be important for us. And in this case, it's a 2. What does that tell us? That tells us that of these 2 strings, the longest prefix suffix is length 2, meaning these 2 first characters match these 2 last characters. Even though the whole string actually matches each other, we're only going with 2 for now, and you're about to finally see why. Because now that we're looking at these next 4 characters and still looking at this same needle, we're not going to start at index 0. We're not going to start at index 1 in the needle. We're actually going to start at index 2 in the needle, Because we already know that these first two characters already match these two characters. Yes, we had to chop one of these off because we did have to shift our window to be at the next position, but we still know that the two characters do match, right? That's why we couldn't have done the entire three characters, because we have to get rid of one of them anyway. So yeah, so that's the repeated work that we're cutting down on. You finally kind of get the big idea that we were going for. But that being said, originally our J pointer was over here, but now it has to be over here. Yes, it had to be decremented by 1, but not literally decremented by 1, because now in the code you're about to see, it's going to get a little bit complicated before it gets simpler. But what we're going to say is if J was equal to 0, meaning we were at the beginning of the needle, we're going to handle things a little bit differently compared to if we were in the middle of the needle, and that's going to make sense in just a moment. But for our else condition, where we are not at the beginning of the needle, instead of setting our J pointer all the way back at the beginning, right, instead of setting it equal to 0, we're now actually going to set it to be LPS of J minus 1, right? However many characters we're matching. In this case, we had an LPS, longest prefix suffix, of length 2, so we were able to set our J to be at index 2 because we already knew the first two characters matched the last two characters of the haystack matching portion. Even though our J pointer is over here now, right, we don't have to go through these first two characters, our I pointer is still over here, right? We were looking to match this X character, and we're still looking to do that. We can't just skip this X quite yet. Okay, so now we're going to continue to the next iteration of the loop. We're going to check, is J equal to I? Again, they're not equal to each other. So again, we're going to run our else case. And again, J is not equal to 0, right? And now it's equal to 2 in the second position. So we're going to again set it equal to LPS of J minus 1. LPS of J minus 1 means at index 1. And just for the context of this problem, this character is being compared to this character, meaning that these two characters, as we know, already match these two characters over here, right? What's the longest prefix suffix with this string? It's 1, right? This matches itself. So now that our J pointer is actually going to be pointing over here at this second character, what that still tells us is, even though, yes, we shifted our window by 1, and now we're comparing this with the X character, we still know that the first character of this is equal to the first character over here, so we don't have to re-look at this first character. That's what the LPS saved us. But as you're about to see, it can't save us forever, because now we're going to run the condition again. We're going to run the loop again. Does this A equal this X character? Remember, our I pointer is still going to be pointing at the X. They're not equal again. Now we're asking, what's the longest prefix suffix between these two characters, which do match each other, right? This string, it's 0, right? Basically our J minus 1. It's 0. So now, as we shift our window one more time, now our window is shifted all the way over here. Our J pointer is actually going to be over here at this first character. So now at this point, you might be wondering, is this about to go forever? Like, how are we going to fix this? Our J is over here. It's still not equal to the X. So what exactly can we do? Well, that's where our if statement over here comes in. We have an if J is equal to 0, right? What can we do now to stop this from running forever? Well, logically in this drawing, what we would want to do is still shift our window by 1. Right now we want to look at these next 4 characters, so this is actually not even available anymore. So clearly, since we can't shift our J anymore to the left, what we're going to do now is just increment our I pointer. And now you can finally breathe a tiny sigh of relief, because that's the entire algorithm except for one last thing. And I'm actually going to slightly change this example because, as you can tell, this is never going to match anywhere in this string. So let's actually change this X character to be equal to an A character. So right now our I pointer is over here, J is over here. These characters do match each other. So we simply increment both of the pointers by 1, as you can see on the left side with our code. Again, they match each other, so we increment them by 1 to the next character. Again, they match each other, so we increment them by 1. And the last characters also match each other, so again, we increment them by 1. So right now both pointers are actually out of bounds, but let's change the example a little bit more. Let's actually add a last character in the haystack. But what we found is that we reached the end of the needle, even though we didn't necessarily reach the end of the haystack. That means this while loop is going to continue to execute, but we don't want it to execute. As soon as we find a match, we want to be done. We know we found a match because we reached the end of the needle, because j is now equal to the length of the needle. It's out of bounds. Therefore, we found a result. Therefore, we want to return the first index that we found that result. Since this is where we found the first matching substring, we want to return the first index of that matching substring. Basically, we're going to take our I pointer, which is over here now, minus the length of the needle, which is going to bring the needle from over here to be shifted all the way to the beginning of that substring. So let's do exactly that in the code. If we found a match, we can return I minus length of the needle. So that's what we're going to do. And remember, in the problem description, they say that if we don't find a match, we just want to return -1. So let's do exactly that. Oh my God, that was probably the longest problem, the longest video I've ever created, but I really hope that it was helpful. Let's run the code to make sure that it actually works. Let's run submit. Okay, so it does work, and as you can see on the left side, it's relatively efficient. Thank God it works, because I would have been pissed if it didn't after recording this for so long. So I really hope that this was helpful. Let me know if you reached the end of the video, and if it was helpful, please like and subscribe. It really took me forever to create this video, but I think it was overall worth it. I know a lot of people requested it, and hopefully I'll see you pretty soon. Thanks for watching.